Dark energy is dying. That is not a metaphor. That is not a dramatic reading of uncertain data. That is what the largest three-dimensional map of the universe ever created is telling us right now. And if the map is right, then everything we thought we knew about how the universe ends is wrong. For 25 years, the answer was simple. The universe would expand forever. Galaxies would drift apart. Stars would burn out one by one. And trillions of years from now, the last light in the cosmos would flicker and fade, leaving behind nothing but cold, empty, infinite darkness. Scientists called it the heat death of the universe. It was bleak, it was accepted, and it was probably the safest bet in all of physics. That bet is no longer safe, because new data from an instrument in the Arizona desert, an instrument that has measured the positions of nearly 15 million galaxies and quasars, is now pointing toward a future that nobody predicted. A future where the universe doesn't fade, it collapses. Not in some unimaginably distant era, within a calculable number of years. A Cornell physicist has already done the math. According to his model, the universe will stop expanding in roughly 11 billion years. Then it will start shrinking. And about 9 billion years after that, everything, every galaxy, every star, every atom will collapse back into a single point, the way it was before the Big Bang ever happened. The universe, it turns out, may have an expiration date, and we may be living closer to the middle of its life than the beginning. To understand how we got here, you need to understand the one thing that controls the fate of everything that exists, and that thing has a name nobody can explain: dark energy. If you've never heard of dark energy, here's what you need to know. It makes up about 68% of the entire universe. Not 68% of the stuff in it, 68% of everything. All the stars, all the planets, all the gas and dust and black holes and galaxies you've ever seen in any photograph, from any telescope. All of that visible matter accounts for roughly 5%. Dark matter, the invisible stuff that holds galaxies together, makes up another 27%, and the remaining 68%? That's dark energy, the majority shareholder of reality, and we have no idea what it is. What we do know is what it does, or at least what we thought it did. In 1998, two teams of astronomers were studying a specific type of exploding star called A, Type 1A supernova. These explosions are useful because they all blow up with roughly the same brightness. So, if you spot one in a distant galaxy and it looks dimmer than expected, you know it's farther away than you thought. Simple. Both teams, working independently, expected to find that the expansion of the universe was slowing down. That gravity, the pull of all the matter in the cosmos, was gradually putting the brakes on. What they found was the opposite. The expansion wasn't slowing. It was speeding up. Galaxies weren't just drifting apart. They were accelerating away from each other. Something was pushing the universe apart, and pushing harder, every second. That something got the name dark energy. Not because scientists understood it, but because they didn't. The word dark in physics just means we can't see it, and we don't know what it is. Dark energy was a label slapped onto the biggest mystery in the history of science. And for finding it, the leaders of those two teams, Saul Perlmutter, Brian Schmidt, and Adam Riess, won the Nobel Prize in Physics in 2011. After the discovery, the simplest explanation was that dark energy was a cosmological constant, a fixed amount of energy built into the fabric of space itself. Einstein actually predicted something like this back in 1917, when he added a term called lambda to his equations of general relativity. He later called it his biggest blunder and removed it. Turns out it might not have been a blunder at all. For 25 years, the cosmological constant fit the data almost perfectly. Dark energy was constant, steady, unchanging. The same amount of push per cubic meter of space, yesterday, today, forever. The universe would expand forever, and the ending was already written. Heat death, fade to black, story over. Except the story wasn't over, because somebody decided to check. In the mountains of southern Arizona, on a ridge called Kitt Peak, there's a telescope that doesn't look like much from the outside. The Mayall telescope has a 4-meter mirror, which is decent but not extraordinary by modern standards. What makes it extraordinary is what was bolted onto it in 2019, an instrument called DESI, the Dark Energy Spectroscopic Instrument. DESI is essentially a galaxy mapping machine. It uses 5,000 tiny robotic positioners, each one thinner than a human hair, that can swivel independently to point at 5,000 different galaxies at the same time. Each positioner feeds light from its target galaxy into a fiber optic cable, which carries that light to a spectrograph that breaks it into its component wavelengths. From those wavelengths, scientists can calculate how fast each galaxy is moving away from us and how far away it is. Do that for millions of galaxies, spread across billions of light years, and you get something no one has ever had before. A 3-dimensional map of the universe's expansion history. Not a snapshot, a timeline. A record of how fast the universe has been expanding at different points over the last 11 billion years. The first round of results, called Data Release 1, came out in 2024. It was based on 1 year of observations and covered about 6 million galaxies. The findings were intriguing but inconclusive. There were hints, whispers really, that dark energy might not be constant after all. Then came Data Release 2, published in March 2025 and based on 3 full years of observations. Nearly 15 million galaxies and quasars, more than double the previous dataset. And the whisper became something louder. Here's what DESI found. Explained simply, imagine you're watching a train pull out of a station. For the first few minutes, it accelerates, going faster and faster. You'd expect it to either keep accelerating or at some point level off and maintain a steady speed. What DESI's map showed was something like a train that accelerated hard out of the station and is now very gradually starting to slow down. The engine isn't dead. The train is still moving. But something about the power driving it forward is weakening. When DESI's team combined their galaxy map with other measurements, the cosmic microwave background from the Planck satellite, supernova data from multiple surveys, and gravitational lensing observations, the picture became clearer. A model where dark energy changes over time fits the combined data better than a model where it stays constant. The statistical preference for evolving dark energy over the standard cosmological constant reached 2.8 to 4.2 sigma, depending on which combination of datasets was used. For people who aren't statisticians, let me put that in plain language. A 3 sigma result means there's roughly a 99.7% chance the signal is real. A 4 sigma result pushes that to 99.99%. The gold standard in physics, the threshold where you can officially call something a discovery, is 5 sigma. DESI hasn't reached that line yet, but it's standing close enough to see it. And with every new year of data, the evidence has gotten stronger, not weaker. Willem Elbers, a researcher at Durham University who helps crunch DESI's numbers, was more specific. He said that as data gets more precise, they are finding potential cracks in the model and realizing they may need something new to explain all the results together. Something new, not a tweak, not a patch, something that replaces a 25-year-old assumption about the most abundant thing in the universe. Now, if dark energy is just a cosmological constant, then the future is heat death, eternal expansion. Everything flies apart. The universe gets colder and emptier until physics itself becomes meaningless. That's been the default answer since 1998. But if dark energy is weakening, if the force that's been pushing the universe apart is slowly losing strength, then gravity, which has been losing the tug-of-war for 13.8 billion years, could eventually win. And that changes everything. Henry Tai is a professor emeritus of physics at Cornell University. He spent decades working on theoretical particle physics and cosmology. When the DESI results came in, and when the Dark Energy Survey in Chile published findings that pointed in the same direction, Tai saw an opportunity. Two observatories, one in the northern hemisphere, one in the southern, were telling the same story. Dark energy is not a constant. Tai and his colleagues, Hoang Non Lu and Yu Cheng Chu, built a model. They proposed a hypothetical particle, an ultralight axion, an incredibly low-mass particle that would have behaved exactly like a cosmological constant in the early universe, driving expansion just the way we observed. But over billions of years, the axion's energy slowly bleeds away, and underneath it, hiding all along, is a negative cosmological constant, a force that doesn't push things apart, it pulls them together. Think of it like a campfire. The flames are the axion. While the fire burns, it pushes heat outward, warming everything around it. But the fire is slowly dying, and behind the fire, the cold night has been waiting. Once the fire goes out, the cold rushes in. Not slowly. The cold was always the default state. The fire was the temporary one. In Tai's model, the universe is currently 13.8 billion years old. It will continue expanding for roughly another 11 billion years. During that time, dark energy's push will weaken. The expansion will slow. Eventually, it will stop. And then, the universe will begin to contract. Slowly at first. Then, faster. Over the following 9 billion years, everything will fall back inward. Galaxies will stop receding and start approaching. The cosmic microwave background will blue shift, growing hotter instead of cooler. The temperature of the universe will climb. And in the final moments, all of space, time, matter, and energy will compress back into a single point. Ethan Siegel, an astrophysicist who writes extensively about cosmology, published a detailed analysis in April 2025, just days after DESI's latest results, arguing that the case for evolving dark energy is weaker than it looks. His core point is that the strongest evidence comes from combining multiple datasets, DESI's galaxies, Planck's cosmic microwave background, and supernova surveys. Individually, each dataset is broadly consistent with the standard cosmological constant. It's only when you combine them that the signal for evolving dark energy appears. And Siegel argues that the tension between those datasets, small disagreements in what they independently measure, could be creating an artificial signal. The data might not be telling us dark energy is evolving. It might be telling us that one of our measurement tools has a subtle error we haven't found. Slava Tereshev, a physicist at NASA's Jet Propulsion Laboratory, raised a similar concern. He pointed out that if supernova brightness measurements are off by even 0.02 magnitudes, a tiny error almost impossible to detect, it could explain the entire discrepancy without needing to change anything about dark energy. So there are two camps. One says the signal is real and strengthening. The other says the signal is a ghost created by combining imperfect data, and neither side can prove the other wrong. Not yet. That's where the next generation of instruments comes in. NASA's Spear-X mission is surveying the entire sky in infrared. And the Vera C. Rubin Observatory in Chile, which started operations recently, will conduct a 10-year survey generating the widest, deepest time-lapse of the universe ever made. Over 20,000 new supernovae host galaxies with precise distance measurements. Every one of these instruments is designed, in part, to answer the same question. Is dark energy constant, or is it changing? If DESI's signal is real, these instruments will strengthen it. If it's an artifact, they will kill it. Either way, within the next 5 to 10 years, we will know. The contraction itself, when it begins, would be gradual. Distant galaxies that are currently racing away from us would slow, stop, and then begin drifting back. The cosmic microwave background, which currently fills all of space at a temperature of about 2.7 degrees above absolute zero, would start warming up. Slowly, over billions of years, the universe would grow denser, hotter, and more crowded. In the final stages, everything would compress at accelerating speed. Stars, galaxies, galaxy clusters would merge and combine. The temperature would climb past anything the universe has seen since the first moments after the Big Bang. And at the very end, time and space themselves would cease to have meaning. Some physicists have speculated about what happens after a big crunch. One idea, called the Big Bounce, suggests that the collapse could trigger a new Big Bang, a new universe, born from the death of the old one. A cycle that has perhaps happened before and could happen again. Thanks for watching, and I'll see you in the next one.